Let's look through some relatively simple examples of Haskell statements, their results, and a little bit about types in Haskell. So for these statements, I'm doing them in GHCI, the interactive interpreter, where you can simply type values or type expressions and they'll get evaluated and something will get returned for you and the return value will be displayed. So for example, just the number 42 is an expression. Its value is 42. 5 times negative 1 has a value. It's negative 5. It's worth noting that I put parentheses around the negative 1 here because the precedence rules will sometimes make it so that a negative is not applied right away. Since the minus sign has lower precedence than a lot of things, it will try to apply the times to the minus operator, because we'll see eventually that we can apply functions to functions. And so we put the parentheses so that it doesn't get confused about the precedence that we want it to do there. You also, in the interpreter, get this free variable called it, which is the place where the result of the most recent expression is accessible. So you can use it to refer back to whatever the last result was. This can sometimes help you to get a little more of sort of an iterative feel and sequential sort of feel to Haskell statements. But you shouldn't get too used to it because inside of your actual programs, you're not necessarily going to be able to do this kind of changing value thing. So it can be helpful, but it also can mislead you a little bit on how Haskell is going to work. So for instance, when I did the 5 times negative 1, not only did I get the result negative 5 here, but it now refers to negative 5 as well. If I use it in a calculation, in an expression, it's going to have a new value the next time. So you can see that negative 5 that we saw here plus 2 is negative 3. Well, now it will be negative 3. And so now I'm saying negative 3 plus 2, and it will be negative 1. Again, not the most Haskell-ish sort of way, not the most functional way to do things, but it can be useful to refer to the result of the last expression that was done. Here's a list. It's a list of numbers, and when we write that as an expression, we get that same list of numbers back. We can also examine the types of different things in Haskell. So if I examine the type of 5, it's set to be the number type or a numerical type. You'll notice that when there's sort of room for a type to be more general, Haskell will leave it more general. So, for instance, fractional and integer are more specific than the number type, but here it's not clear whether 5 needs to be a decimal type of number or an integer type of number, and so it only infers that it's a number. And it then names some type A to talk about that numerical type that we've seen before, rather than having to repeat that over and over again and to save some ambiguity if our statement had multiple types in it. 5.2 will have the fractional type because it needs to be more specific. It's clearly fractional. It clearly has some decimal value to it. The string text, well, strings are just lists of characters in Haskell, and we can treat them just like lists, and we'll see that later as we're working with lists. The type of true, notice that it's capital T in Haskell, is bool. And here, I'm actually naming a value. I'm saying let v be a name for this stuff on the right-hand side of the equals sign. The stuff on the right-hand side here, in this case, is a tuple, which is a grouping of values. And that tuple contains a string and a list with 2.3 in it, therefore a list of fractionals. You see when I ask what the type of V is, it says it's a tuple. That's the parentheses and the comma. And that tuple contains an array of characters, also known as a string. And it also contains a list of t's. Well, what is t? T is some fractional. And it names it t so that we can refer to it if it shows up multiple places in here or things like that. We have a couple of convenience functions that relate to tuples. They typically are viewed to be pairs, and so there are some convenience functions to give you the second item from a tuple, which is that list with 2.3, or the first item from a tuple. Typically, we're only really interested in accessing the first or second. There are good ways to deal with longer tuples, and we'll see good examples of those later. Let's look at some conditional statements too. So if I name a value x and a value y, which are 7 and 10 respectively, then I can make statements like, if x is greater than y, then the string greater will be my result, else the string less will be my result. All expressions in Haskell have to have some kind of result. We've perhaps seen ones that are IO results or things like that are different types of results, but every statement needs to have some result to it. This statement has the result of one string or another. The types of the results from a conditional statement, like if, else, have to match. I can't say in one case it's a string and in another case it's a number. So these have to match in terms of types. It's almost like a return statement because whatever I've said in my then is going to be a possible result, and whatever I've said in my else is going to be another possible result. I can take the result of that if-else statement, put it in parentheses, and do stuff with it, like combine it with another string. This plus plus will allow me to combine lists, and strings are lists of characters, and so we're just taking whichever of the two strings comes out of this, combining it with space value, and we get less value as a result. So conditional statements are themselves expressions with a value that they result in, one or the other of these, and we can use those expressions and sort of nest them in other longer expressions too. Here I'm naming a value a, and I'm saying if x is greater than y, then x will be what a gets, else y is what a will get. Well, we know that x is not greater than y, so a is a name for 10 now. And since we discussed that we can nest if-else statements inside of other expressions, then it will only stand to reason that we're able to nest an if-else inside of the then part or the else part of another if-else. So here, for instance, I say if x is greater than 20, then 7 is a result that way, else we have some complicated result to it. And you'll see this is the same with or without parentheses, because else is just going to say, go ahead and give me whatever result is here. Well, to figure out that result, we have to evaluate the if statement that's sort of nested there. And I could have nested an if statement here where I have 7 as well. They're just expressions. They're going to give a value as a result, and therefore they can be nested inside of lots of various places. I could have even nested something as part of the expression for the if here to say if x is greater than, and then some if that would give me a result that would be the right-hand side of my greater than evaluation there. So they can be nested in any place that a value could be put because they're an expression that will result in a value, just like x plus 2 or just like 20. Here are some standard functions, and I want to talk a little bit about how operators work in Haskell. So Simple infix expressions like 5 plus 3 are definitely allowed. You'll see that 5 plus 3 results in 8, as you would expect. Most functions in Haskell, though, fit the prefix style, sort of like what you're used to in a Python or a Java, where the name of the function comes first, and then the operands come after. And we can even make our infix operators behave that way. If we put them in parentheses, then we're able to say things like plus 5, 3, and we are giving the what is the function, and then its parameters, and we get a result from it. We can do infix with other operators like usual, division, subtraction, etc. Division by default works on fractionals, meaning that it will do floating point division. There is a special div function that does integer division. So we say div 5, 2. Just like I could take plus, times, minus, or even divide and put them in parentheses and make them a prefix operator, like I did with plus up here, I can do the opposite with a prefix function like div. I can put single quotes around it, and now it becomes an infix operator. So I can say 5 single quotes div 2, and it will result the same way that div 5, 2 did before. So those single quotes switch it to being infix notation. The parentheses will switch an operator to being prefix notation like we did for the plus up here. So if you're more comfortable with one or the other, you can switch things around. I would recommend getting comfortable with the prefix notation because that's sort of the default for most things in Haskell. If you use infix for the built-in operators like plus, minus, times, divide, yeah, fine, that's okay. But it's probably best to get used to this prefix notation for functions, at least. Double equals is another operator that can be used to check equality. And you'll notice that it doesn't specify that it has to work on integers or that it has to work on strings or anything like that. It works on types which have equality. So if a type is able to have equality checked for it, which is this EQ type, then we can use double equals on it. Or slash equals, which is not equals. So be careful not to do the exclamation point equals you might be used to in other languages. It's slash equals here. But both of these are perfectly fine operators. And just understand that the type that they will require is an equality type, a type for which equality can be checked. So this statement is saying that double equals uses some equality type as its parameters, and we've called that A here, or rather the type inference system has called that A here, and that it results in a bool, true or false. Print is a function that you can use to print out or display things. You'll notice that it works on the number 3, it works on strings, but there is, when we say print a string, it prints it in the sort of native representation, meaning it keeps the quotes included. If we want strings printed more in the standard way that we're used to for output, without the quotes around them, then there's put string or put string line. This one will introduce a new line. If you leave off the ln, it will not introduce a new line. So we see that we give it the word as a string, and it removes the quotes, or rather it doesn't print it with the quotes. It just prints the word, and then would have a new line after it. It does have a very strict type because it only applies to strings. If you want to use something like a number with it, you'll need to convert that number to a string first. The show function can be useful for converting a lot of different types of values to strings. So you can then say put string or put string line on that result that's given from the show function. Lists will be extremely important to us in Haskell. You've seen a few already in the examples we looked at. Simple ones like brackets 1, 2, 3. These are pretty easy to deal with. You'll also find that it's easy in Haskell to give ranges and enumerations. You can give sort of a default incremental range, 10 ... 15 will go by increments of 1, 10, 11, 12, 13, 14, 15, and it gives you that full thing as a resulting list. You can also indicate to Haskell what the step should look like. So here I've said 10, and then my next value is 12. So the difference between these two is 2, and therefore the difference between every step in this is going to be 2. So you can see that it's 10 through 20, but it's counting by 2s, 10, 12, 14, 16, 18, 20. And we can do that with different step amounts if we want to. We can combine lists using the ++ operator. This requires both sides to already be lists. So this is not helpful if you have just a standalone item that you want to have combined into your list. The single colon operator will take a value that's not in a list and combine it with a list. Again, all of these will require that the types match inside of those lists that you're combining, or between the item that you want combined into your list. The types will, of course, have to match. So these are ways that you can grow a list or sort of append to it. You also can use some of the built-in functions for getting values from the list or getting parts of the list as well. The most common examples of that are head and tail. These get a little tricky, especially for those of you who are familiar with the language of head and tail around, say, linked lists, where the head is an element and the tail is also a single element. That's not going to be true here, and it's not true in a lot of functional languages. Head, yes, is a single element. It's the first thing from a list. So if I ask for the head of this list 5, 6, 7, the head is just the number 5. But the tail is more like a remainder of a list. This makes it helpful to be able to do something with the first value and then recursively call for the rest of the values after the first, for example. That's a pretty common usage of the head-tail kind of structure. So here, tail of 1, 2, 3 is the list 2, 3. And even if there were only 2 items in the list, for instance, if I said tail of 2, 3, the tail would be the list containing the number 3. It would not just be the element 3. So be careful to remember that tail will be a list while head will be a single value. We can combine these just like we'll be able to do with any function. We're able to call head on the result of calling tail. So the parentheses here provide us precedence on this. And so it will say, get the tail of 1, 2, 3, which we've seen would be the list 2, 3. And then once you've done that, get the head from that. And that is why 2 is the result from this, because tail sort of chops off 1 and gives us just the list with 2, 3. And then head will grab the 2 from it, and that will be our result. We can index into lists as well using 2 exclamation points and a number. So here at index 1 from the list 1, 2, 3 is the number 2. We could do that with any valid index there. I want to point out at this point that there's another useful operator that we'll use well beyond just when we're using lists, but I want to show it to you here because it can be a useful way to kind of combine steps with what you want to do with lists, but it can be useful to combine any two functions. The dot operator will take two functions and combine them. The other term for this is function composition. We're combining or composing two functions into a new one. So for instance, tail returns a list. Well, head works on lists. So it's okay to compose these two functions as long as the return type of one is, or the resulting type of one, is the input type of the other, the parameter type of the other, then we're allowed to compose them. So you'll notice this takes something that goes from B type to C type and something that goes from A type to B type, and it sort of jumps from A to C. So it's really the same as what I did up above with head parentheses tail, except for this gives me a new function that I don't have to retype head parentheses tail a million times. So I've called this HT, and it takes the head of the tail of a list. So if I give it the list 1, 2, 3, it will take the tail first and get the list with 2, 3. And then it will take the head of that result, which is the number 2. So we'll see this in the future for combining functions, composing functions into new functions. But using head and tail was a convenient way to show that off. And you may want to do this relatively often with different list functions. So here are some other pretty standard list functions that you might want to use. Null is a function that checks whether a list is the empty list. And so you can see that it's false for 1, 2, 3, but it's true for this empty list here. There are some other functions that will let you check features of the items inside of the list. So any is a function that you can give it some criterion in the form of a function, and you can have, it will tell you if that criterion is true for any of the values inside of the list there. So you can see that I'm asking, are there any that are greater than 3? Interestingly enough, you can give this sort of partial statement here because greater than is a function, and it will take two inputs, two numbers. And so we've partially applied it here, and we're able to then have any apply it to each of the items inside of my list there. And likewise, I can check if there are any that 3 is greater than that number. So there are not any that are greater than 3 in this list, but there are any that 3 is greater than them in this list here. Now, we can do this, a similar thing with all. I can check if all are greater than 3. That's certainly not true. None of them are greater than 3. And I can check if all are such that 3 is greater than them. This should have a false after it as well. It seems like it didn't get included there. There are these other very helpful and hopefully will become very familiar to you functions for approaching lists in Haskell. They're very common among functional programming approaches in general. Because we do so much with lists and we focus so much on taking some input and doing something and getting some new result with it that we then might be able to use to do something else and get some other new result, we have these functions map and fold that will be very useful to you in relation to lists. So map will take some function and it will do it to all items in a list and give out a list of results from that function being done to every item in the list. So you give it some function. Here I've got a partially applied +3. So it's going to take whatever it grabs from the list and do +3 to it. And then the result I get is a list where everybody has had +3 done to them. We could map head onto this list of lists, and it will give me the first item from each of the lists inside of this list. You'll also often see nested lists like this, sort of like a 2D array almost. And so we've applied head because the input type of head is a list. And this over here, every entry in the bigger list is a list. So I'm allowed to apply head to this first list. I'm allowed to apply head to that second list. And I'm allowed to apply head to that third list. And I get out the heads of each of those lists. So map is a great way to take a group of values in a list and do something to all of them and get a new result. If you had strings here, we could maybe trim away all the spaces using map and get a new result from that has each of those strings with the spaces trimmed away, or different things like that. Another really helpful map function is folding. You can choose to fold starting from the left, or you can choose to fold starting from the right. Those are named fold L for starting from the left and fold R for starting from the right. I'm sorry, I just indicated left and right backwards. So folding starting from the left, which is what you might be more used to, starting with the leftmost entry. Or if you need to, for various reasons, you can choose to fold starting from the right, sort of reverse stepping through the list there. And so what fold does is it takes a list and it applies some function and gets a resulting value. So that function's going to need a starting value, and then it will apply with that starting value and the first entry it gets from the list. It will then take the result of that and apply it with the function and the second element from the list. It will then take the result from that and apply it with the function and the third element from the list. And in the example shown here, we only have 3 elements. So it takes 0 plus 1, gets the 1, and then takes the 1 plus the 2 that's here, gets the 3 from that, takes 3 plus the 3 that's the last element in the list, and gets the result of 6. So folding can be a really good way to take all of the stuff in a list and get some result from it, get some, process through all of it. Getting sums, getting averages, different things like that can be ways that we would use folding, and certainly plenty more advanced ways as well. Not shown here, but also very helpful, is the filter function that allows you to take a list, apply some Boolean function to it to check a criterion, similar to what we did with any and all. We can filter for only the ones that meet some criteria so that we could limit down to only the important ones from a list, for instance. There is a map version that works on monad functions, which is the Haskell way of talking about void functions that don't return any value for us, don't result in any real value. They result in this sort of nothing value, such as printing. So if I wanted to print out all of the strings in a list, then I can apply map M, and it will allow me to execute that monad function on everything in the list and not worry about the fact that it doesn't actually come out with a value for each of those, like we would expect a normal map to do. There are lots and lots of other list functions available. For some of them, you may have to import the data.lists module to get those functionalities available in your programs. I want to show you a few common errors that people often make when working in Haskell or in functional languages in general. Some of these sort of apply broadly. One common error is using the wrong combination method between two things to try to make a list. For example, plus plus only takes a list and another list. It cannot take a simple value like 3 here. If we had put 3 in brackets and made it a list, then the plus plus would work. Or if we had used colon up here, then this statement would work. 3 colon the list 5 would work perfectly fine. I've shown the errors you'll get because the language for them can be very strange, and so this might be a good helpful reference to you to come back to if you see an error that you don't understand. So here's another common example, is taking a list and the colon and another list. These especially happen when you're getting like the result of a function and trying to combine it with something in a list, because you don't remember perhaps that that function actually resulted in a list, not a single item, or that kind of thing. And so it can be easy to forget what types you're really combining. And therefore, if you see these kinds of error messages, you might reconsider whether you're using the right combination method there. Another common error is thinking that you can return or you can result in different types inside of a conditional. Again, especially if what you've got here is some named value, some variable, or is the result of some function or more complex expression itself. Mismatching the types within a conditional will lead to big problems, because Haskell needs to know that this expression results in blank particular type. And so it can't be 2 types. It has to be one specific type that if statement results in. Another common error is, I've hinted at this in a couple of different ways, but particularly common is trying to do head, tail, and then a list. You know you want the head from the tail of the list, but Haskell doesn't know that. Haskell looks at what you've stated here, and you've said take head and apply it to the function named tail. And so the types don't match there, because the function named tail is not the right kind of input for head. Head doesn't take functions as its type, as its parameter type. It takes lists. And so here, parentheses would help, or doing that dot operator to combine head and tail if you're going to be doing this often. There are lots of ways to avoid this. Parentheses are probably the easiest. Make sure that whatever follows head is the exact thing that head expects as input, which is the result of tail on that list, not the tail function. And this will happen for the negative symbol. When you try to say plus -5, it tries to apply plus to the function minus. And similar problems will arise as you list out functions that you want applied. It tries to apply the first function to whatever immediately follows it. So parentheses will often be necessary. There are lots and lots of jokes about the number of parentheses you need in Haskell or other functional languages, and there are ways to avoid them and make things cleaner too. These last 2 examples on this slide are ones that are really, really common for people coming from other languages like Java and Python, where you can just take strings and do plus and combine them. Plus is an operator for numbers. It will not work for strings. Plus plus is an operator for lists, And since strings are lists of characters, plus plus would work in this example and combine these two strings. But plus simply will not. And similarly, plus is not magic like it is in many other languages. It will not magically convert 5 into a string. Neither is plus plus magic. You cannot just say string plus plus a number. But you could use the function show or various other methods to convert the thing that you have over here, like the number 5, into a string, and then use the plus plus operator to be able to combine them. So now you've seen some basic syntax in Haskell, some common operators and functions. You've seen a little bit about how you can use those functions in interesting ways, combine them, and how the precedence of those functions can lead to possible downfalls for you. And you've seen a little bit about lists, and we'll get more expert on those. It's also a topic that you probably want to play around with and get more familiar with, and check out some of those more advanced list functions too that are available in the data.lists module, and you can find those in the Haskell documentation. We'll keep moving forward here in the future, looking at more and more advanced options in Haskell, but there are plenty of good resources out there, and I hope that you'll try things out yourself too.